This week we're talking about the mid-latitude weather. The mid-latitude where we lived. So it's an area of transition. You think about it up towards the poles. We looked at the global picture and they basically are cold almost all the time. About 60 degrees north, we have that belt of low pressure that typically moves there. Around 30 degrees south, we have the highs that sit there. Well, we're between them. So what you wind up with is a transition back and forth of low pressure coming in, high pressure coming in. So I wanted to just look at a little bit of this in terms of what's current now. So this is an analysis. And what we have on it is surface pressures and 850 millibar temperatures. Anything in blue in the 850 millibar temperature is basically 0 Celsius or below. Anything in red is above that. They're basically 3 degrees apart, plotted. This is a forecast model. However, the analysis of it is pretty accurate. So let's just look at this in terms of air masses. Everything starts with an air mass, right? That's where we change air masses. So if you think about it, air masses are typically at the center of high pressures. So if I'm looking at the high pressure that I'm seeing up here just south of Hudson Bay, high pressure is 1028 here, 1031 here. 850 temperatures are, well, here's minus 21, minus 27. So what kind of high pressure would that be? Probably an air mass would be a continental polar air mass. So it's dry because it's formed in Canada. If I were to go back, I could see this high pressure was originally developed up in Canada. And Canada doesn't have a lot of moisture around, so it's another high pressure that has very little moisture with it. So it's continental and it's polar. Now, I want you to look off the coast here. Off the coast of New England, well off the coast, is another high pressure. Well, that high pressure is formed out over the middle of the ocean. Now, the ocean is kind of moist, isn't it? So it's a maritime high pressure air mass. And now here comes the complicated part. The further north it is, if they form up over the northern Atlantic, they're probably going to be polar. If they form down over closer to 30 degrees north, they might be tropical. This one looks like it's more up towards the north, since high pressure is up there. So we're going to call it probably maritime polar. That's a fairly cool air mass. Now, there is high pressure down over the Gulf of Mexico and all that you can't see very well here. And that high has formed in the tropics, so it's maritime tropical. You'll notice just in talking here, we've defined 3 different air masses. Where do those air masses come together? Well, think about any front that we have is going to have an area of low pressure or lower pressure along it. Here is a cold front. Here's the low pressure, extratropical low pressure sitting up over New England, north of New England. There's another low pressure that's over the Bahamas. Between them is a polar front, a cold front. It's separating this continental polar air from maritime polar here. So we have a cold front. Now, there's another one right here. Here's low pressure. We know the flow around low pressure is from the south. It's counterclockwise, so we've got it south on the eastern side of it here. Well, notice how these isobars go out. They kink. So there's lower pressure along this line right here. That is a warm front. It is separating maritime tropical air to the south, continental polar air to the north. So now you've just looked at the weather map and you've just picked out fronts where the air masses probably originated, and 2 extratropical low pressure systems, one sitting here over Colorado and one sitting just north of Maine in Nova Scotia. They're extratropical lows. So we're going to make sure we understand those as well here, because I wanted you to know that extratropical low means we have temperature contrast. So look at this. On one side of it, we have plus 6 degrees Celsius. And on the other side of it, I'm all the way down at least minus 15, maybe minus 21. There is a very strong temperature contrast here. These form along areas where the fronts are. The same holds out here. At this low, we have a very strong temperature contrast to the east of it. The reasons you don't see anything plotted to the west of it, these are the Rocky Mountains, and they actually go up above 850 millibars. So I just wanted you to get a feel for these. I can go out and look at how this is going to evolve with the pattern here. So if we were to say, oh, this is a initial, supposedly, analysis for 8 a.m. today. So let's look 8 a.m. tomorrow. So we'll go there. We'll come back to this a second here. And we'll move out into the future. And we'll go out 24 hours in the future here, hopefully. There we go. And 24 hours. We will get a different looking picture now. I want you to think about how these things have evolved. Remember, we had a low up over Nova Scotia. We had a low over Colorado. Well, what do we have now? This is 24 hours later. That low that was over Nova Scotia is gone, but there is a new low. Remember, we did have low pressure. It was off the Bahamas. Well, now that same low has moved up to off the mid-Atlantic coast. High pressure, it's kind of split in two. We have one high sitting out to the west of Hudson Bay, and we have another high that's now over New England. A very strong high, actually, over New England, 1043 millibars. Both of these are continental polar highs. Oh, yeah, low that was over Colorado, it's now over Kansas. That warm front that we saw here probably has now moved further north, probably kinking up into here, maybe even coming up through Ohio, West Virginia some. Along the East Coast, that very continental polar air mass, northeast winds coming in. What are you going to get? You're going to get cold air advection into this area. So we have cold air coming in on the east side of the Appalachians. So this is how these patterns work and evolve with time. I want you to understand these are extratropical lows. These are not tropical. They have nothing to do with tropical low pressure. When there's a temperature contrast across them, they're extratropical low pressures. Now, tropical lows can evolve into them, but they may not. So when you do your discussion this week, please refer to the extratropical lows. And you can see we have several on this map. Oh yeah, interestingly, if I were to take this low here, moving up off the East Coast, and say it went into New England, well, probably bring a lot of rain, right? It's got a lot of moisture with it out here from the Atlantic and the tropical Atlantic and stuff. However, if I move it over here, there's no precipitation for New England, just high pressure. So just small shifts in track can make huge differences. So I wanted to show you now a little bit. Well, now that we've talked about this, let's look a little bit into these slides here. And we'll try to start right at the beginning here. But we're going to move through pretty quickly because I've talked about a lot of what we're going to pick up this week. So here we have all of our weather systems. Here are the different air masses. I talked about those, where they form. Think about it. If you wanted to form an air mass that was continental tropical, you would look for desert location, something that's hot, humid, and dry. Not hot, hot and dry. So where would that be typically formed? Well, typically out over the southwest U.S. Air masses will modify. Obviously, think about it. If I have an air mass that's coming out of Canada and you had snow on the ground in Ohio, okay, when the air mass is moving down, it's modifying some, but it's not modifying a lot. However, if I didn't have snow on the ground in Ohio, for example, or in West Virginia, what would happen to those air masses? They're going to modify a lot faster. And because of that, they're going to be a significantly warmer air mass than the temperatures that they had up in Canada. Probably a good thing because I don't want to be that cold. And another thing, tropical air masses don't tend to modify as quickly as continental polar air masses. That's because the ground tends to stay cold, warmer, and helps to keep them not changing as fast. So, stationary fronts. That's a front that's not moving. Every one of the fronts I showed you today was pretty much moving along some. The one off the east coast of the United States may or may not have been stationary, but because of the new low coming up on it, it's probably moving along some. But remember, warm air is lighter than cold air, so you get the warm air rising. Most of the precipitation is going to, in a stationary front, is going to be on the cold side of it. However, there is right along the front on the warm air side, there may be some thunderstorms and all with it. Here is a warm front. Again, the air is moving north towards over that boundary. And the further into the cold air, you might actually have snow coming down. And gradually, as the warm front approaches, it transitions into rain. So you can see how temperatures were gradually warming up as the warmer air gets thicker and thicker. Oh yeah, if you actually have some of that, you could actually have some freezing rain in parts of it too as well. Cold air is very dense, so we know that the front goes up pretty quickly in a cold air mass. If you're flying in an airplane and you go across a cold front, you're going to see that cold front extend much further up in the atmosphere very quickly than a warm front. You could probably fly into the warm air for quite a ways before you finally hit into the colder air. Fronts can move all different directions. This is a backdoor cold front coming down the east side of the Appalachian Mountains. Notice in 24 hours from now, they have a large high pressure system up over New England. That is actually pushing the cold air down, and it is causing literally almost like a backdoor cold front that has pushed through the eastern United States. So there are also occluded fronts. At the end, towards the end of a cyclone's, extratropical cyclone's life, the cold front catches up to the warm front that was there out ahead of it. So think about it. There's warm air on the east side of the extratropical low, cold front to the south of the low. As it takes its time, that cold front's moving faster than the actual low, and it's also moving faster than the warm front. So it eventually pushes through and lifts that warm air aloft. When that happens, you have an occluded front. So the warm air is literally aloft at that point, and you have two different air masses, but they're both relatively cold air masses. If one side, the advancing side, is colder than the other side, that's a cold type of occlusion. Very normal in most of the eastern 2/3 of the U.S. On the West Coast sometimes, however, you get a warm type occlusion. What that means is the colder air is on the east side and the warmer air is to the west coming, even though it's still a cold front or occluded front in this case. All right. Back in World War I, they conceptualized what an extratropical low pressure system should look like. And this concept that still holds today. Initial low pressure develops along a front. Think about it. The low is developing, so you get counterclockwise winds. So you're pulling cold air down here to the west side and the south of it. you're pulling warm air up. You're actually increasing the temperature gradient here as you're pulling these closer together. And as it gets stronger and all, you do more of that. What I really wanted to show, though, is notice the cloud. You'll see literally it looks like a comma. And the more intense it gets, the more that shape develops until it finally gets a very significant comma head at the end of it. And here is your occluded front, moving right along in this part. So they develop the later you get into the cyclone's development. So there's another way of looking at extratropical cyclones, and that's what we call the conveyor belts. So in an extratropical cyclone, there's a warm conveyor belt tropic out of the tropics and up along the east side of the low. There's also a cold conveyor belt that comes up and out of the north to the north, drops down, and lifts up over the low pressure system. It's ahead of the warm air actually rises up and over the cold conveyor. When that happens, that's where a lot of the precipitation occurs. It's also how the comma head occurs. That cold air moves westward, past the low, and then comes back and tilts back to the northeast as it's rising. So that whole layer of air is rising up, cooling, causing precipitation, and it forms a comma head to the west. Now, I wanted to think about lows, extratropical lows, and where they move. We have gotten tremendously better in forecasting them. However, once in a while we do make mistakes. And when that happens, you don't have to be off by a lot. So on the east side, typically is all rain. Warm front coming up, maybe some thunderstorms even, typical of the pattern. West side, more no colder air. And especially if you stay west of the low the whole time, you're going to stay in the cold sector. So you'll probably have snow. So if that low shifts slightly one way or another, you may be in the warm sector or you may be in the cold sector. And it can make a huge difference in what your precip is going to be. Lows move all over the place and form. Some of the biggest ones form out of the Gulf of Mexico and come along the east coast. One of the things about extratropical cyclones is the greater the temperature gradient, the better chance it's going to be a strong low. Well, on the east coast in the wintertime, you have Arctic air that comes out of Canada, comes into the east coast. Over the ocean, you have a Gulf Stream. So you wind up with very cold Arctic air coming down to the eastern part of the United States and very warm, literally tropical air on the Gulf Stream. You wind up with extreme temperature contrast, and that's why you get these very intense lows along the east coast, typically called nor'easters many times. Here is just another case of showing just small changes can make huge differences in the forecast. Cold core, it means it gets colder with height. Extratropical lows are cold core. So yes, as you go up, the system gets more intense and the temperature is going to drop. Sometimes you get a little weaker ones, aren't quite as occluded. Warm core is very different. Warm core means it actually warms, fairly warm in the middle of it. You wind literally with high pressure aloft over top of these lows. They're mostly thermal lows. Hurricanes are a warm core system as well. There's two other breezes we wanted to talk about quickly. Sea breezes. We've talked about them. What happens with the sea breeze is you wind up heating the land during the daytime. Air rises. The air's got to come in to take its place. We know the atmosphere doesn't like a vacuum, so it comes in off the ocean. At night, it gets colder over the land. Air sinks because cold air sinks, moves back out over the water. Valleys have the same kind of wind systems, just based on where the mountains and all are. Chinooks are sinking air that comes down typically on the east side of big mountain ranges. Some Chinooks in the United States occur in Colorado or Wyoming, even Idaho. And when they occur, sometimes they can be called snow eaters because the temperature will warm 50, 70 degrees sometimes and just eat up the snow as that air is sinking down over the mountains. Santa Ana winds are another form of that as well. So if you're in Los Angeles and the big high pressure has developed over the basin out to your west, all of a sudden some of that air gets over top of the mountains. Gravity will help to pull it down into the LA basin. It's sinking, it's drying. Remember, it's getting less and less humid with time as it sinks. So you wind up with very hot air, very dry air that's come down into the basin. That's why they have a lot of fires with them. So I think that's what we're going to stop with right there. I hope you got a little bit out of this. And please let me know if you have any questions